Hello everyone, dear group members. I'm so excited to present my project to you. It's going to be about the energy quantization with respect to the advances which they have been made, I should say, in the field of quantum physics and quantum field theory. I have prepared my presentation in three different parts. The first part is going to be a very brief introduction that what is a quantized energy. And the second one, I'm just going to get involved into a little bit, I should say, of some technicality. And at the end, I'm just going to talk about one of the brilliant advances which they have been made. And as you can see, for example, from this one here about the lasers, how can we just harness the advantage of quantized energy concepts in quantum field theory to just talk about the lasers and find the lasers in many different applications around us. You see in the picture which I have here, let me change the color. You see in the pictures which I have on the top here, we have, I should say, a laser which is done, I should say, which have been applied into, I should say, one of the telescopes at the NASA in order to correct the deflections of the light from, I should say, the outer planets. On this picture here, you're going to see the Schrödinger cats. I'm not going to talk about this, except the fact I'm just going to use this formulation of the Schrödinger equation. And also, I'm going to talk about the oscillation. It's the thing which we have seen around us in all, I should say, in many different things, in different, I should say, appliances, many different concepts, even from the high school physics. Okay, and now, let's get back to some kind of technicalities. And what is, I should say, the quantized energy and why we just have to incorporate the quantization of the energy into our daily scientific life. Look at the pictures which I have on the left side. Picture A, picture B, picture C. In all of them, I have one, I should say, substance, which it has a mass of the M. And as you can see, at the equilibrium points, we do not have any stretches or contraction of, I should say, of the spring, which has a constant and the rigidity of the K. When you push, I should say, the force to contract the spring, you see that the force of the spring is going to work, I should say, in the opposite direction of the contraction. And when it goes, I should say, passes the equilibrium points here, you see that when the x is positive, it's just going to come back again to the other direction. And that's why we have defined the Hooke's law in, I should say, in the elementary physics from the high school. In the quantum physics, when we just want to just have a concept of the quantized energy, we still work with these simple harmonics. We call them simple harmonics oscillators. And you see, I'm going to talk about this picture a little bit later, that what these, I should say, wavy, I should say, fields, they can be interpreted, but still, I'm just going to start from the classical physics and find the quantized energy at the end. You know that in the classical physics, we can talk about the total energy, which comprises, I should say, from the kinetic energy of this, I should say, oscillating mass. I'm just going to call this the kinetic energy as 1/2 of its mass times its velocity squared plus the potential energy which this oscillating object is going to have. You know that from the Hooke's law, you can derive the potential energy, which is going to be the potential energy due to the contraction of this spring, as 1 over the rigidity of the spring squared times, I should say, x squared. You can say sometimes delta x, which it refers to the distance which you have, for example, from the equilibrium points to, they call that the displacement. And that's defined, I should say, the total energy from the classical perspective. All we have written here, it's going to be the classical perspective, and now we just want to just leap into the quantum field and quantum physics to see how it's going to be modified. In the quantum physics, the energy is going to be transferred and transformed into an operator. Operators are the objects in the quantum physics when they can act on a state of the matter in order to extract new information from it. And now in the quantum physics, the energy that we have, it's going to be looked at as the Hamiltonian, and the Hamiltonian is going to be written as p squared divided by 2m P is going to be still, I should say, the momentum, linear momentum, which is going to be m times v. And if you substitute that, you see that you get still the 1 over 2 mv squared. And I do still keep 1 over 2 kx squared. However, in the quantum physics, we look at everything as an operator. By the operator, I mean that the energy Hamiltonian becomes an operator. I showed that by a kind of a simple hat on the top. And the momentum is going to be an operator, and also displacement is going to be looked at as the operator. There are some, I should say, the technicality that we have to just use, I should say, the Schrödinger equation, which is going to be the I as an imaginary unit, h bar, the constant Planck, I should say, the partial derivative with respect to the t of, I should say, they call that psi, kit with a Dirac notation of a wave equation should equal to, I should say, the Hamiltonian of the h, which I described it here at the state of the particle, which is we call that kit of the psi. In order to just get there, we have to just put h hat in terms of, I should say, some operators. I'm not going to talk about that in details because it's going to be too much things to talk about. But remember that for the p in the quantum physics, they replace it with the IH bar, a partial derivative with respect to the x. When you do that, you can just come and see that you can simplify that into, there are many steps to take because you have to just incorporate also the annihilation operators and increasing operators. I'm not going to talk about that, but at the end you end up with this one, that the energy of the system is going to be n plus 1 over half h bar omega. It is a Planck's constant, and the omega is a radial frequency of the oscillator, which is oscillating back and forth with respect to the equilibrium points there. And that's the thing which is, I should say, has a tremendous interpretation to that. And I'm just going to spend a couple of seconds before I just go to the applications of the quantized energy to talk about this. And as you will see from this equation which I have, n is a quantized number, and that's where the quantization of energy comes from. N can be any number. N can be 0, n can be 1, n can be 2, n can be any natural number. Imagine that when you have any number assigning to the n, and that's how you just talk about the quantized energy. That comes in contrast with the thing which we had before. In the classical interpretation which I had on the top, this energy is a continuous spectrum. The energy of this oscillating object can be anything and takes any form. But with this quantum interpretation as an operator, imagine for n can be discrete number, and the discreteness of this n number gives rise to the quantized energy. And now imagine that if you take n equal to 0, you get the energy of the quantum state becomes 1 over 2 h bar omega. And that's interesting in quantum physics, which you cannot see something comparable to that in classical physics, and that's what they call that zero energy, which it means that even when the object is not moving, oscillating in quantum physics, still you can assign an energy to that. In the classical physics, you couldn't, because if the object is not moving, the kinetic energy is 0, there is no displacement, and the total energy is going to be 0. But in quantum physics, even at rest, at the zero state of the matter, the objects can have energy, and that's what they call that the zero energy. That's something which only happens in quantum physics. And now, I think that's enough of, I should say, of the concepts of the quantized energy, and now I'm just going to talk about the application. A very brief introduction about the application, which is going to be the concepts of the lasers. I'm just going to talk very briefly. In the concepts of the lasers, we are going to talk about the quantized energy. Why? Because if you look at that, for example, if you imagine that the matter has two states of the energy, I call that the energy here as a ground state, and I call that the energy on the top as an excited state, or the second state. And the difference of the energy, I just call that delta E. How the laser works. Imagine that if this is going to be a laser here. You have something which it has two mirrors, and you have a laser medium. It's a medium that you are going to excite at the atomic level the atoms in that, I should say, the laser medium. It can be ruby or it can be anything but something which can be excited very easily. And now you shine a light inside. For example, the energy comes with the h nu of, they call that the incident photon, and comes inside and excite the atoms of the laser medium. Then the atom from the ground state goes to the excited state, and because here it's unstable, it transits back to its previous state. But how this happens? These transitions from the excited states to the ground state, it comes with the emission of the photon. The emission of the photon is quantized. It's going to be the discrete difference of the energy states of these two levels of the energy in the laser medium. Because of the quantized energy, we know that this difference of the energy should not be continuous. It can take only discrete value, which they call that h nu. H Planck constant, nu is the frequency of the photon which is emitted, which is a function of the difference of these two states. And now imagine that you started with one photon and at the end you got two photons. And imagine that because of the mirrors that you have here, because of the mirrors, when you have one photon here, it gets reflected back from the other mirror and goes back again to the medium. It excites more atoms. And the more atoms are going to get excited, the same cycle happens. And again, you have two photons there before, and now you get at the second stage, you get three photons coming out. And these three photons again are going to get reflected back from this mirror and go back to the same medium, to excited medium. The same cycle of the excitation and relaxation happens, and again, from three photons, you may end up with 6 photons. And that's what they call that as amplification. That you start with one incident photon or incident radiation captured and confined inside a cavity of the lasers, but because of the discreteness of the energy which governs quantum mechanically the radiation from, I should say, the emission from an excited medium to its ground state medium, then this quantization allows you to amplify the energy of one photon and get billions, I should say, of the radiation captured inside this. And after the process of the amplification, and that's why you can see that the lasers beams, they are narrowly focused, coherent, and they have lots of energy there, and they use that in, I should say, in the applications. Okay, now, I should say I have lots to say, but the problem is that I do not have enough time, because I think also I exceeded some time. I hope that you saw what is, I should say, if I'm going to go back to the thing which I plan to do, I hope that you understand about the concepts of what is a quantization of the energy. You understand about the zero energy in terms of, I should say, working from the classical physics going to the quantum physics by using, I should say, the concepts of the simple harmonic oscillations. And at the end, you just got the concept, I should say, of the laser, I should say, in the applications from the thing that we talked about in my project. Thank you very much for listening, and I do look forward to hearing your feedback then. Thank you, and have a wonderful day.